Hello everyone, I am Yao Lingdi. I will introduce baselines for facial image ordering sub-challenge. My presentation will include baseline models, experiments, and further improvement. We propose two solutions for facial image ordering. We know makeup is a typical process that we constantly apply cosmetics to our face. We can recognize the overlay changes even without knowing the makeup actions. So our first model is only based on images, ignoring the influence of step description. It provides prior bias for facial changes during makeup process. The second baseline is text-aware image ordering. It takes step description into account, which can provide additional guidance to understand facial changes. We can express a makeup step as a visual equation, which means a raw facial image as an influence of a step description is equal to a new related image. The pipeline of our solution includes two stages. In first stage, we train two models in different metrics, and in second stage, we apply the models to sort images and select a final answer. Next, I will introduce the baseline models in detail. For image-only solution, we design an image pairwise comparison model as shown in the figure. This model is a Siamese network. It includes a twin image feature extractors and a binary classifier. The input are two facial images, image I and image J, that belong to two different makeup steps. The output is class 0 or 1, which indicates relative order of two images. If image I occurs earlier than image J in the video, the ground truth label is 1, otherwise it's 0. Text-aware method, we formulate the ordering task as a compositional image retrieval problem. The query is composited of a source image and a mode text. The source image is the facial image between aligning the makeup step, and the retrieval target is a facial image after the makeup step. We utilize a state-of-the-art compositional image retrieval model, which can be denoted as TIRG. The input of the model is a triplet, and the output is a feature matching score. This model uses texture embedding to modify source image representation, and pushes the modified image feature to be closer with the target image feature in the vector space. You can refer to the original paper for details. Now, we have had two baseline models and can train them on the YouMakeup dataset. During post-processing stage, we need to use a trained model to select an answer. For image-only method, we first get all pairs in a candidate answer, then sum and average their occurrence probability. Finally, we select an answer with the highest score. For text-aware method, it will be a little complex, because we don't know the correspondence between images and text. Thus, we can't construct triplets directly. Generally, we pick an initial image first and iteratively retrieve the next target image by grading algorithm. Then, we will get a sequence of target images. Finally, we pick an answer with minimal edit distance from the target image sequence. Now, I will introduce the experiments part. Because our two baseline models are trained on images, so we firstly do data pre-processing. Specifically, each makeup step description is aligned with a video clip, and we extract 10 frames at the end of each video clip as trained images. Emphasis on the end is to ensure that the facial appearance has changed after the related makeup step. For image pairwise comparison model, we randomly select two images from two makeup steps in a video as an image pairs. Note that we balance the classification labels 0 and 1 in construction. For TIRG image retrieval model, we randomly split multiple step descriptions in a video into n parts to construct triplets. Now we will move on to the experiment results of two models. For image-only method, since it is an image pair classifier, we use algorithm as metric during training process. And in post-processing stage, we use multi-choice selection accuracy to measure its performance on facial image ordering tasks. As this table shows, the classific accuracy of the image pair classifier is higher than 80%, which means sorting two images is not difficult even only with image information. On the other hand, the choice selection accuracy on test set is less than 70%. This means that simple comparing visual appearance can't solve our image ordering task well, because in our task, the model needs to sort multiple images with a variance or slight difference. Intuitively, if we apply more makeup steps, the facial appearance change in images will be more obvious, thus easier to sort the images. So we further explore whether the step gap make an influence on the results. Here, we define the number of interval steps between two images as step gap. As shown in this table, the larger step gap is, the easier to distinguish facial difference and the better classification performance gets. Based on this discovery, we utilize a curricular learning strategy to train the model. Here, this strategy can be summarized as a simple idea that we train model from easy examples to hard examples. Specifically, we divide the training data into three parts based on step gaps. During training process, we train our model on the divided three parts data. As shown in the two tables, the curricular learning strategy can slightly improve the model performance. Next, I will introduce the results of a text-aware model. Because it is a retrieval model, we use recall at rank k as metric. From the following table, the TIRG model outperforms random retrieval with large margin. The image-to-image in third line means we directly use source image feature to retrieve target image feature, ignoring the step description. Comparing the second line and the third line, we can know that the modification text does play a guidance role. Unexpectedly, the performance of TIRG model is less effective than image pairwise comparison model in the multi-choice ordering task. We analyze there are two main reasons. First, the post-processing strategy of text-aware model for ordering is not optimal. We need to split the given steps into several parts, which are noisy. Second, the current text-aware baseline only uses coarse-grained features and lacks efficient textual guidance. Different from image pairwise comparison model, the TIRG model is better in small step gap, since it might be hard to capture long-range facial changes. Therefore, image-only and text-aware methods complement each other when we considering the step gap between images. Finally, I will introduce some further improvements from three aspects. For the architecture, since facial image ordering is a novel challenge, we can explore more novel solutions. The idea of text-aware baseline can be seen as a visual addition formula, and how to composing image and text representations is crucial in this problem. On the other hand, the core problem can also be seen as a subtraction formula, which naturally builds a relationship between a step description and the facial appearance difference. Under this architecture, characterizing facial difference on makeup is important. Meanwhile, it is crucial to learn fine-grained interactions between text and images. As for features, since baseline models only use a simple feature extractor, it has a lot of room to improve. Finally, from a more fine-grained level, we can consider two sides. On the image side, it can be helpful to detect different facial areas and objects, and check their continuous changes. In the meanwhile, be careful about the unrelated disturb, such as postural variation. On the text side, the accurate face area annotation of each step can be taken into account for improvement. In conclusion, the proposed baseline models make a baby step on the facial image ordering task. This novel task has much room to be improved and explored. Welcome to pay continuous attention to our fine-grained dataset and challenges. Thank you for listening.
Hello everyone, I'm Lu Dan from Renmin University. I will introduce the baseline of sub-challenge, step ordering. For this sub-challenge, we use two kinds of model to build the baseline. First, since the YouMakeup dataset sets multi-choice selection as test pattern, from where the text options contain the sequence information of makeup steps already. In order to test the influence of information in this part, we first use the plain text sorting to do this task. We set the first model a pairwise text classifier, given two-step descriptions from a video, embed words with glove, and then employ a bidirectional GRU to encode sentences. We average hidden states of the GRU as the final sentence embedding, input the two sentence embeddings to a multi-layer perception network, and output their order. For training data, we shuffle ordered steps in given training set to build pairwise sentences. The classification performance is broken down by step gap. See this table. Steps with smaller gap are harder to be ordered correctly. It's intuitive because adjacent steps are more likely to be reversed during the makeup process and cannot simply be ordered by prior knowledge. We will introduce how to use this information in test phrase later. The second baseline model makes use of video information. Since the correct order of step descriptions correspond to the video timeline, temporally aligning each step description in the video can solve the step ordering task. Therefore, we formulate the core task as temporal activity localization via language, given an untrimmed video and a step description. The goal of temporal activity localization via language is predicting the start and the end timestamps of description corresponding to the video. We adopt one of the state-of-the-art models, Semantic Conditioned Dynamic Modulation (SCDM) as our baseline model for the TALL task. This figure presents the overview of the SCDM model. Briefly introduce it. In first stage, we cut the video into 1-second clips, extract features by pre-trained model, fuse video features with embedded descriptions. In second stage, we use temporal convolutional model to capture temporal contexts. There are also some treatments for multimodal alignment. For more detail, please refer to the baseline paper or original paper. The third and the last stage is prediction model, which outputs matching score and corresponding time duration. Due to the fine-grained nature of makeup videos, it might be beneficial to employ more fine-grained supervision to train the cross-modal alignment model. Therefore, we employ the grounded facial area in training phrase, as YouMakeup dataset provides corresponding facial area of each cosmetic description. In prediction model, for each predicted positive candidates judged by matching score, we propose to utilize the corresponding feature in a multi-label facial area classification task. To apply the above two kinds of baseline models, pairwise text classifier and SCDM-based model on multi-choice selection, we set different strategies. For pairwise text classifier, we calculate the score of each candidate following the formula and pick one with highest score. The hyperparameter alpha is defined by step gap. The greater the gap between the two steps, the higher the confidence of the classifier, and the greater the fraction of the score alpha. To apply the temporal grounding model in test set, firstly, we generate an order of shuffled textual descriptions via the model. Then, we calculate the Levenshtein distance between the predicted order and each candidate. We pick the candidate with the shortest distance. Now I will go to the experimental part. In the experiment, for TALL assignment, it has its own metric, rank n. It is defined as the percentage of sentence queries having at least one correct moment retrieval in the top n retrievaled clips. The higher the number, the better the model. We compare two widely used video features, C3D and I3D. Both features of YouMakeup dataset are released online. The results are shown that I3D features are more effective than C3D features. Furthermore, comparing SCDM Plus and SCDM, utilizing facial area as additional supervision can boost the localization performance. which demonstrates that it is beneficial to make use of grounded and detailed information in the fine-grained localization task. However, compare the video-aware model with the text-only classifier. The text-only baseline achieves a surprisingly good ordering performance. One possible reason is that the strategy of using video-aware model on ordering tasks might be less effective than that of using text-only model. In our additional experiment, when the text-only model uses the same ordering strategy, it achieves much worse performance, which is not shown here. To exploit the bottleneck of SCDM-based model for further boosting of the performance, we make statistics and visualize the specific performance of the SCDM class on the validation set. It can be seen from the figure that for nearly 40% of the validation set data, the IOU of model's predicted time period and the fact time period equals 0. In other words, in many cases, the model detects the video time period completely wrong, corresponding to the text, which is non-ignorable. In order to further exploit the reasons of detection failure, we first analyze the model's recognition effects on different facial regions. There are totally 24 different facial regions. We counted their recall rates and the IOU promotion in validation set separately. We find that the performance of the model varies from different facial areas. Taking some of the facial regions as example, the recognition effect of jaw is the worst among them, for which the recall rate is only 0.22%. Of the further statistics of the training data distribution, we find that there exists long-tail problem seriously. The training duration of certain categories is extremely low, like jaw, mouth. Their IOU even becomes lower after additional supervision. In order to test the detection ability of the model on cosmetics, we conducted case analysis artificially. First of all, the model lacks the ability to recognize similar cosmetics. In the first example, under the guidance of ground truth, apply blush on the cheeks with brush. The model is positioned in the contour part. The actions and the corresponding facial areas are quite similar for these two makeup steps. The difference is that blush makes the corresponding area red, and the contour makes the corresponding area dark. Similarly, in the next example, when the ground truth is apply eyeliner on the end of the lashes with a pencil, the model confuses it with brushing long eyelashes. The facial area where these two actions apply is similar. Both are in the eyelash area. The tools used are all pen-shaped. We expect the model to distinguish the effects of different makeup steps. Don't be fooled by similar actions and similar beauty tools. Another problem is that the model lacks the ability to contact other text descriptions. One of the manifestations is that there are cases where two steps are mapped to the same interval. In specific example, for description, apply light cream eyeshadow all over the lids with finger. The model locates quite accurate compared with ground truth, while in another case, model locates apply concealer all over the lids with finger in the same time period. This could be better if the model takes all the step context into consideration. Summarize the directions we can improve in future work. Firstly, consider using sequence information from multi-choices. When we turn the task in the form of localization, we lose quite accuracy in test phrase due to the loss of sequence information from multi-choices. This direction is task-specific but effective. Secondly, solve the long-tail distribution problem of training data. It is a normal problem in classification area, and this task also suffers from it. Thirdly, improve the model's ability to recognize cosmetic in fine-grained level. Our base model is actually not fine-grained enough, which only take the motion features of videos into consideration. Last, improve the model's ability to align other text steps in the same video. Compared with purely localization problem, other steps may help improve the final performance. Thank you.